Hello, people. Today we're going to continue our discussion and on the calculus part. The next topic that we're going to discuss is backpropagation. And it's a quite important topic for machine learning research, and it will be covered in the details in this lecture. So for training deep neural networks, we usually use backpropagation algorithm, and it's an efficient tool to compute the gradient of the error function with respect to parameters of the models. Why we compute the gradient? Because when we compute the gradient, we can apply then optimization algorithms such as stochastic gradient descent or ADAM or ADAGRAD in order to tune these parameters of the neural network. And this is what it's called training of neural network. So the crucial component of that training is the ability to compute the gradient of the loss function with respect to parameters of the model. And this is exactly where the backpropagation technique will be useful. So let us recall how we compute the feed-forward step for the neural network. We have input X, and we now consider the first layer of the neural network associated with the weights formed by matrix W1. So we take this input X, we pass that input X through that first layer, and as a result, we, as we previously actually showed, we have output, which is the product of weight matrix associated with that layer transpose multiply on X. Then we add to this the bias vector U1 associated as well with the first layer of the neural network. And then what we do component-wise operation by applying activation function to it. And as a result, we got this vector F1, which is a vector, and it's now used as the input to the second layer. And after that, we basically keep repeating the same procedure for the subsequent layers as well. So what we have in a nutshell, it's a basically recursive procedure that allows you to construct a sequence of vectors, starting f0 of x, starting with x, with the input itself, and then each subsequent output fi of x is nothing but activation function applied to this expression that uses this input of the input to that layer, which is output of the previous layer. So we have this recursive expression that basically guided the feed-forward computation of the neural network. And now we typically associate, for each layer, we combine all the parameters associated with that layer in one structure. Typically, it's a vector as well. So here, theta1, it's a combination of vectorized version of matrix W1 and the bias vector U1. Theta2 is a vectorized version of matrix W2 and bias vector U2, and so on. And finally, theta k is a vectorized version of matrix WK and bias vector UK. And then we combine all these theta1, theta2, and theta k in one huge vector, which is basically called the parameters of the model. Like this theta, it's something that we will need to basically tune during the training of neural network. Now, how do we tune that? Yeah, so we typically start with some observed data set. Here we can see the supervised learning regime. We have data with the labels, and the ability of the neural network to feed that data typically is characterized by a fitness measure, usually defined through the loss function. So here the loss function basically tells how far the output of the network, which is this guy here, this vector fk, the output of the last layer of the neural network, evaluated on the data points x data from the label y data that we should observe in that according to that observation data set we have. Therefore, in order to compute the gradients with respect to this parameter theta, what we need is we need to take partial derivatives with respect to each of these theta j, which is associated for each layer of that neural network. So for each j from 1 to k, and this is where we will apply the chain rule. for differentiation. So if we have a nested compositional function and we want to take a derivative with respect to parameters associated with let's focus on the kth layer. We want to take the derivative associated with the kth layer. We firstly take the derivative of the function with respect to output of that layer, and then we take the derivative of the output of that layer with respect to these parameters. Now the same strategy works with the layer next before the last one. So in order to take the derivative with respect to in order to compute the partial derivative with respect to weights associated with the layer k minus one, we firstly compute the derivative with respect to output of the k layer. Then we compute the derivative of the kth layer with respect to k minus one layer, output of the k minus one layer, and then we take take the derivative of the output of the k minus one layer with respect to the weights associated with that layer, and so on. What you can see is that we can actually split this computation in several stages. So the orange terms here are partial derivatives of the output of the layer with respect to its input. So keep in mind that for the kth layer, the output is vector fk, but the input is fk minus 1. And the fk minus 1 is the output of the k minus 1 layer. Next, the blue terms here are the derivatives of the output of the layer with respect to the parameters associated with this layer. And these are the blue terms. And you also can see that if we calculated the derivative with respect to parameter g plus 1, then most of this computation can be reused in order to compute the partial derivative with respect to theta j with the weights associated with the previous layer. So it's we can see that indeed here, because as you can see, the only thing that we'll have to compute when we do the computation backwards, starting from the k, then k minus 1, k minus 2, and so on, is basically these two terms in these green boxes, while everything else we can reuse. And this is the idea of the backpropagation. Now we're gonna look more carefully on this derivation. Here we actually put that as exercise, but we decided to explain it in more details because it's very useful to see how it's actually conducted. So consider now the example of backpropagation for the following K-layer network. So we have the input x, we have first layer, which output f1 of x, vector f1 of x, then and so on. Then k minus third layer, k minus 2 layer, k minus 1, and k. And then finally we get the value of the loss function here. So we can see that this simple neural network that has k layers, and we already know that the output of the layers, basically they form this recursive structure presented here. And now let's see how we can compute the derivative. The first derivative that we're gonna focus is we're gonna focus on the kth layer, the last layer, and let's say we take a derivative with respect to this weight. So ij entry of the matrix wk associated with the last k layer of that neural network. So I know that, okay, in order to compute that derivative, we need to compute that derivative of that loss function, and that loss function uses as an input the output of that layer, fk of x. And that output of that layer is itself a function that depends on that parameter with respect to which we want to compute that derivative. Which because this parameter is an entry of that matrix wk. So then, following the chain rule, we need firstly take the gradient of the function with respect to the output fk, and then we need to take the derivative of this vector function fk with the corresponding parameter that we want to, with respect to which we want to compute the partial derivative. Okay, so following the definition, the first factor in that product is nothing but just the gradient of the loss function with respect to output of k, and it's constitute that dk dimensional vector. Dk here is just the dimensionality of the output of the k layer. So the output of the k minus 1 layer will be dk minus 1. The output of the k minus 2 layer will be dk minus 2, and so on, just for notational convenience. Now, when we need to compute the derivative, the second factor in that product, we need to compute the derivative of the output of the kth layer, so vector of k, with respect to this wij entry of the matrix. So following the form of the output of the k layer, which has this form, now this differentiation will apply that we need to compute the derivative of this vector function, which is component-wise applied activation function with respect to this term here. Now let us take a closer look how this computation will take place. So now we're going to focus on this second factor term. So as we had previously, it's nothing but partial derivative with respect to that vector function, and that vector function is we know that it's activation function applied to each component of that vector, omega k transpose of k minus 1 plus uk. So therefore we basically write it component wise as presented here, and we can rewrite it further in this form presented here, where we just we decompose this matrix vector product as in terms of this matrix entries. The reason why we do that, because we need to eventually compute the partial derivative with respect to entry of the matrix, and that's why we'll have to break it down in this form. Just keep in mind that for this derivation here we miss the bias uk. Actually, it should be presented regardless of the fact that we don't take the derivative with respect to it now, but it will take a role when we compute the derivative of this activation function. So it's a slightly typo here. So basically, keep in mind that here in the argument of this activation function, it should be always plus uk. Plus uk plus the first component of uk plus the j component of uk, and so on. Yeah, and typically as activation function, these are the most popular choices that are used in machine learning. Specifically, this GLU function is the one that is used in transformers nowadays. So they are most of them are differentiable. Like with the ReLU case, it's not differentiable at just one point, but everywhere else is differentiable. So therefore, in order to compute that derivatives, we need to take the derivative of the activation function and multiply on the derivative of the input of the activation function with respect to that parameter. But please notice that because we take the derivative with respect to ij entry of the K matrix, the only term, the component in that vector that will contain that ij entry, it's exactly that component here. Neither the first nor others will not have this ij. So therefore, basically, when we'll take the derivative with respect to inputs for these components with respect to ij, it will be nothing but 0. So that's why we have everything everywhere 0 except this component. And in that component, as you see, we need to take the derivative of the activation function evaluated at this component here again, plus the corresponding bias. Multiply on the derivative of the input of that input with respect to ij, and the derivative of that input with respect to ij, because it's just a summation. It will be nothing but the corresponding ith component of the vector fk minus 1, because all other components will be multiplied on the other entries of the matrix wk, and not on the ij entry. and because we take the derivative with respect to ij entry, they will filter out. So hence we can derive that the derivative with respect to of the loss function with respect to ij entry of the K-layer can be broken as using the chain rule as a product of these two terms, where the first term is the gradient. And I also should specify that here is just missed. It's a typo where we missed the partial derivative operator sign. So here should be delta everywhere here. And multiply on the corresponding derivative of the output of the K-layer with respect to ij entry of the weight matrix. Now we're gonna store this vector in our memory. We will have this expression here. And now let us now go one layer back and consider the now partial derivative with respect to this parameter, which is ij entry, but of the matrix associated with the k-1 layer. And now we will see how we're going to reuse this data that we basically described previously in this backpropagation slide. So now, because we have two layers, so in order to take the derivative with respect to k-1, ij of k-1 layer, yeah, we have of the loss function that depends on the output of k of the k layer, which is itself depends on the output of output fk-1 of the k-1 layer. So we have this double nested structure here, and only this inside function depends on this ijk-1, wij-1 with respect to which we want to compute the derivative. Following again the chain rule, in order to compute the derivative of this double nested compositional function, we firstly take the derivative of the loss function with respect to output of the k layer. Then we take and that's already in our stored in our data set in our memory. Then we need to take the gradient of the output of the k layer with respect to its input, which is output of the k-1 layer. And then finally, we need to take the gradient with respect to derivative with respect to of output of the k-1 layer with respect to the weights, with respect to corresponding weights, wij k-1. Applying the same strategy that we applied when we compute the gradient, the derivative of the fk with respect to wij, we can immediately write for this derivative this expression where we use the implicit form of the k-1 output with respect to the k-2 output of the k-2 layer, and following exactly the same strategy, we arrive to the similar expression. The only difference is that instead of k-1, we have now k-2, and the reason we have zeros is exactly the same reason here, because the only term, it will be only one component in that vector that will be basically depending on this ijk-1, and this is exactly that component. All others will be zeros. But now the new thing is this Jacobian that we need to compute, which is the derivative of the output of the k layer with respect to the output of the k-1 layer. And let's take a closer look on that Jacobian. Following the definition of the Jacobian, it can be written as this matrix. This is nothing but this definition of the Jacobian that we discussed previously. And now we basically substitute the expression of the output of the k layer with respect to its input, which is the output of the k-1 layer, and it has these expressions here. Now, when we use the fact that each of these guys, it's a compositional function. It's compositional function itself. So in order to compute that gradient, we firstly compute the gradient or derivative, because that's a univariate function. We compute the derivative of the activation function, and then we'll multiply that result, that derivative, on the derivative of the input of that activation function, corresponding input of that activation function, with respect to corresponding component of the k-1 layer. And as you can see, what it can be simplified, this expression, this product can be written in this form, where just for simplicity, we will denote that vector as just a vector of the derivative of the activation functions, component-wise. This is just a vector of ones with dimensionality equal to dk, which is the dimensionality of the output of K-layer. And this is nothing but just a weight matrix associated with the K-layer. So as a result, we have this expression, and that's an explicit form, post-form expression for that Jacobian. And we're gonna store that Jacobian in our memory as well. And now our memory looks like this. So we have this gradient of the function with respect to output of the K-layer, and now we have the Jacobian of the K-layer with respect to the output of the K-layer with respect to output of the K-1 layer. And as a result, now we'll be able to compute the corresponding partial derivative as just basically computing the product. Now let us look one more layer back. Now we're basically focusing on K-2 layer. And let's assume that we want to compute the derivative with respect to ij entry of the matrix associated with K-2 layer. Again, following the fact that now the corresponding parameter will be associated with the K-2, with the output of the K-2 output, which itself will be used as an input for computing the output of the K-1 layer, which itself will be used as an input in order to compute the output of the K layer, which then will be used in order to compute the loss function. Now we have this triple nested compositional function, and therefore, in order to compute that partial derivative, following the chain rule, we'll have to compute these products of four terms. But luckily, this term and the second term already stored in the memory, and the only thing that we'll need to compute these two additional terms. For the very last term in that product, we can compute it following already the computation that we done before, and it's just a derivative of the output of the K-2 layer with respect to this ij entry of the matrix, weight matrix associated with the K-2 layer, and it will have this expression. Exactly, it's keep in mind, remember, like because the only components that will be associated with the ij entry, it's this component here. That's why we have zero other components. And also, when it comes to this Jacobian, which is Jacobian of the output of the K-1 layer with respect to the input of the K-1 layer, which is output of the K-2 layer, we can use the similar strategy as we previously computed in order to compute this expression, and we have this term. And of course, we add that term in the memory as well. And continue in the same fashion. You can see that equipped with that memory, we will reuse all these terms for computing the next partial derivative with respect to more early layers. We will use all these terms that we computed for the later layers, and the only thing that we will need to compute is just these two additional products all the time. And that's the essence of the backpropagation. And that's why now you know why it's called backpropagation, because the computation is more efficient to conduct this computation starting not from the early layers, but starting from the later layers. The last layer, the one before the last, the one before previous, and so on, because you can actually reuse all these terms that you computed before in order to compute the partial derivatives with respect to parameters of the early layers. And and that's why it's called backpropagation. Opposite to the feed-forward phase, where you basically start from the input and you basically feed-forward you compute sequentially from the early layer to the last layer, the output of the neural net. So we have these two procedures: feed-forward and backpropagation. Now, it's important to notice that from practical point of view, backpropagation, of course, it's more time-consuming than feed-forward stage, and typically, roughly, it's 3 times more consuming than feed-forward stage. And based on this observation, there are some work that focuses on computing the works that focus on computing the gradient using not backpropagation technique that we describe here, but more exotic technique that uses the finite difference formulas that allows you to rely only on the feed-forward stages. The reason it's exotic because that requires you this interplay between the corresponding variants that will be introduced, because these techniques typically they are stochastic, and then they require careful consideration of the variance of the corresponding stochastic process. Yeah, but the working horse for machine learning is the backpropagation technique that we just discussed. And that's it for today's lecture. Hopefully it was clear. And guys, if you have any questions, please ask it in the comments, and we'll be glad to respond. And for the next lecture, Professor Haitham Bauman will continue his discussion on the probabilistic related topic. And when it comes to this, it's a last lecture on the calculus part for machine learning. Yeah, and if you have some specific also recommendations, what do you want us to cover next when it comes to mathematical topics, please share it in the comments as well. And thank you very much. Please like and subscribe, and we will be glad to post more videos for you guys. Thank you.